Hi, everybody. My name is Dina. I currently work for Google for the past 3 weeks now. So my talk is based on my previous job at Riverbed, where we did application performance monitoring. So today we're going to talk about automatic monitoring and diagnostics on production, as the title says. So I always like starting my talks with a little motivation. So I'm going to try to convince you why monitoring and profiling on production is very important and sometimes even a must. Then I'm going to present to you my master plan for tackling this self-monitoring plan. And then after all the hand waving, we're going to embark on 3 demos where we're going to see different aspects of problems we can monitor, detect, and possibly even diagnose right there on production. So let's start. As I said, we're going to start with some motivation. So it's pretty clear to me, and I'm actually sure that it's pretty clear to you as well, that it's very, very important to monitor our applications. Obviously, it's a must for basically anything at scale. If you develop a server and you usually have quite a lot of instances, you can't allow yourself to wait for the customer to come and tell you that something is wrong. You have to be on top of things. You have to know that there are problems happening before it causes actual negative value to your clients. And obviously, again, because we're talking here about scale, about large systems, you can't do it manually. You have to automate things. But that's a pretty obvious case. We're not going to talk too much about it. What I want to add here is something that I'm not sure people always think of, and that's that, like, in my opinion, it's just as important to monitor simple desktop applications. And in a sense, it's even more important to monitor these systems because unlike servers, where we usually have access to the systems and we usually have control over what's installed, what other software is running, we don't have any visibility into what's happening on our clients' machines once they install our simple desktop application. We can't access it. We don't know on which operating system it's running. Well, we know if it's Windows or Linux, but we don't know what the version is. We don't know how many hotfixes are installed. We don't know what other software is running there and might be getting in our way. So we really don't have any way to know what's going on there. And it's not until the client calls us and tells us that something is very, very wrong and they're not going to renew the subscription until we realize that, we should have collected some data. And even had we collected some data and we would have known that we were using too much CPU or whatever, we usually, at least from my experience, can't reproduce the problem. Because these, at least from my experience, these are rare cosmic events where software kind of clashes together and causes these big, mishaps in our production, and there's basically nothing we can do about it. So I hope I convinced you that monitoring is important. Why should we build our own monitoring system, though? Because there are plenty of off-the-shelf software for monitoring and profiling software out there. Why should we develop our own? Well, I didn't write this on the slide, but personally, I think that investigating performance is important. So, for me, that's a good enough reason. But on a more practical note, I think that the obviously most important advantage of developing our own framework is that it's going to be specifically tailored for our business needs. It's not going to monitor just this general metrics such as CPU or memory or, I don't know, exceptions or whatever it is. You can monitor your own software using it as a white box. You know what's going on. So you can monitor specific components runtime. You can monitor specific requests. You can monitor queue sizes. Whatever it is that you have in your applications that you know is important and critical for your performance. Another important advantage of having your own framework is that the diagnostics data flows from ground up. And what I mean by that is that you don't redirect the data, the monitoring data, to some external dashboard, wait for something to happen, wait for an alert, wake up in the middle of the night, start scratching your head, thinking, well, what should I do now? No, the application actually gets the data in real time, becomes self-aware, hence the name of the talk, and the result of this behavior is that it can also immediately, in real time, act upon what it sees. And this is something that is not available to us when we do this whole pipeline of data, going to dashboards, coming back to us in the middle of the night, when we don't really want to think about what we need to do next. And lastly, well, in itself, it's not a very good reason, but that's what all the cool things do, right? I think that with the DevOps state of mind of automating monitoring, or basically automating anything, we can't stay behind. And again, in itself, it's not a good reason, but the state of mind became so popular because of all the good reasons that I just mentioned. So we're kind of converging on that. So how do we go about implementing this grand scheme that I have for self-aware applications? Obviously, we can't allow ourselves to have a profiler or a debugger constantly attached to our production. The overhead is just going to be too big. So what I suggest, and I think it's not very new or surprising, is a hierarchical monitoring scheme. So I would suggest that we use our cheapest tools to monitor all the basics, to monitor the things that we need to monitor in the highest frequency. So that would usually be resource consumption. That would usually be CPU usage, memory usage, disk usage, queue sizes, as I said, maybe number of requests, really, again, depending on your application. These are, as I said, numerical data representing resource consumption. On Windows, you can quite easily do this using performance counters, general stuff. These are, performance counters is an API in Windows, which allows you to kind of connect different metrics spread out through the entire Windows system and consume this data about, again, CPU, memory, disk, all sorts of .NET related stuff like GC performance, generations, heap size, stuff like that. If you don't like performance counters, you can use Win32 APIs. Doesn't really matter. All the data comes from there anyway. So that's pretty easy. Then, if there are less frequent events that interest you, such as rare exceptions or maybe deadlocks that you fear might be happening in your system, you can allow yourself to use a little more resources, because the events are less frequent, to try to find out more data about what's going on. So two of the tools which are available to us for this purpose, and we're going to see them later, later during the talk, are ETW and CLRMD. ETW is similar to performance counters in the sense that these are trace points which are spread out throughout the entire system and allow you to connect to them and consume data. But unlike performance counters, the data that ETW emits is not just numerical. So for example, you can get information about types which are being allocated in .NET applications. And you can find out the reason the GC was invoked, and a lot more data like that. So it allows you not just to detect a problem, but it also allows you to collect some information that might help you understand what the root of the problem is. Another tool which is available to us is CLRMD. CLRMD is a library, a .NET library that has been available, I think, for a few years now. It's an open source library developed and maintained by Microsoft. You could get it from NuGet. And it provides a very convenient C# API for debugger-like actions that you might want to do with your application. So you can attach the CLRMD API to your application and start, peeking inside, seeing what it's doing. You can get call stacks, you can get traversal of the heap, you can see what's going on in the memory. And I didn't say this, but it's actually can be used both with native and managed applications. So no matter what type of application you have, you can use it. And the overhead, of course, mainly depends, well, actually for both for ETW and CLRMD, it mostly depends on the amount of work that you want to do and the frequency of the events. So traversing a 64 gig memory space is going to take a while. However, getting the call stacks of a few threads is going to be pretty fast. So the amount of data you're going to collect is going to control the overhead, and so you might apply it in different ways in our grand scheme of hierarchical monitoring. And lastly, if worst comes to worst, and you can't get what you need from ETW or CLRMD or performance counters, there are really heavy-duty tools available for you. That's the CLR profiling API and the CLR debugging API, which really allow you anything that a profiler or a debugger would give you, including stopping the application, going through breakpoints. Obviously, this is not something you could usually do in production, and the documentation itself says that if you have a time-sensitive application, you should not use these APIs. But know that they exist. If you have a really good reason to use them, you can. I have links here for them. We're not going to talk about it today, mostly because there's only so much you can do in 40 minutes. And because, as I said, it's really a huge overhead, and I assume that, 99.99% of the time, you're not going to use these tools. So I think it's not as important to cover them. And lastly, there are also hooks. If there's a specific API that interests you, you can try to hook it. But again, I'm generally advising you against it because it's pretty complicated to do it correctly. And from my experience, a lot of security software also does some hooking, and then stuff tends to get kind of clash together when one of the parties doesn't do it 100% correctly. So it has a lot of downsides, but it's an interesting topic which would deserve a minimum 2-hour talk at a different time. So I think we're done with all the hand waving. We have our motivation, we have our plan. Let's see some of this in action. Let's start with this relatively straightforward scenario of CPU profiling. Although it's generally simple, I think that and it's also not very specific for your applications, I think that alone could add a huge benefit to your production systems. Imagine that suddenly your application is using too much CPU. Okay, you can actually even usually try to understand from the logs the general area where this was happening. Like it was happening maybe in some image processing component, because that's what we were doing at the time, or maybe someone was logging into the server. But these general purpose logs usually won't give you the exact information of which function, which loop, what location in the code caused the large CPU usage. So we'll try to figure it out. And instead of waiting for the customers to call you and saying, hey, your process is hogging CPU, and then you having to either try to reproduce it in your development environment or hope that it's still happening at the client's machine and connect there and try to add a profiler, I'm going to show you how we can in real time on production get this profiling data and just solve the problem immediately. So we're going to act according to our plan. What we can do is monitor for CPU usage using performance counters, just to detect the problem. Usually everything would be fine, but every once in a while our process might get crazy and start using too much CPU. So we could define some sort of rules, like something that's good for our process or something that the client is fine with, something along the lines of the application can't use more than 80% CPU over 10 minutes. Over 10 seconds, sorry, 10 minutes is crazy. So something like that. And once we detect this using performance counters, then we can start a profiling session using ETW. And I didn't say this before, but ETW actually provides us with call stacks for almost each of the events that it can provide us. And so by simply sampling the CPU, it can give us the locations of the functions that the CPU is currently executing. And this would allow us to reconstruct the call stacks and analyze what's going on exactly like a profiler would do. So usually we would collect all this data and then analyze it in development environment using symbols and like all the available tools. But using an open source library available on GitHub called LifeStacks, we can actually do the exact same thing in real time on production, provided that we have symbols, of course, which I know is not obvious, but you have to give something to get all the benefits. And so in real time, we can find hot paths, maybe produce flame graphs, and maybe even suggest some recommendations on what can be done to make the situation better. And if you're wondering what on earth we could suggest in real time to do, here are a few examples. One is if your authentication controller is suddenly overworked, then perhaps you're being attacked. Maybe you're getting a denial of service attack. If some sort of computational component suddenly takes too much CPU, maybe you need to scale your application, your service. In fact, maybe you could even scale it automatically, which would be double the fun. Or at the very least, if you don't have anything smart to say, you don't know what to suggest, at the very least, you could record all the data and send a detailed report to development, which would for sure help the developers figure out what was going on much better. So let's see this in action. So since we don't have a lot of time and demos tend to be a little flaky, I have recorded the demos. So we'll see the application first, and then we're going to look at the code and what we can do. So I have here an application, a website. It's an ASP.NET. I'm going to do something with the website, and I am monitoring here on the right side CPU consumption, processor time, using perfmon, which shows us metrics for performance counters. So let's see what's happening. This is the website. I'm going to try to log in. You can see that CPU is low. I'm logging in, and suddenly something very bad happens while I try to log in. CPU has spiked, has gone down, and that's the end of the video. So obviously, had this happened in real time, I wouldn't have been able to catch it on the spot. There's just not enough time to come with a profiler and connect to it. So there's a huge benefit in automatically trying to figure out what happened right there in production. So let's see how we can do this. So this is the code. Is the font large enough? Cool. So this is the application. We're not going to get too deep into the code again because we don't have much time. Plus, it's all available online, so you'll be able to look at it later. I just want to give you ideas and motivation about what can be done. So here we have the CPU monitor, and the CPU monitor is kind of an event stack monitor, which is itself a type of monitor. Now, I do have to mention now that I'm not 100% sure that, architecture-wise, this is the best design. So don't go, copying it to your systems. Think about it a little before. It's okay if you do, but I didn't invest too much time into thinking about it. In any case, this class monitor encapsulates the concept of doing some lightweight monitoring using performance counters and then invoking some sort of intensive sampling function once something bad is detected, once we pass the thresholds which are defined in the monitor. So basically what this class has is this timer, which samples the performance counters, and once it passes the threshold for a certain amount of times, it just starts the the intensive sampling, which is implemented in the subclasses. So let's go back to the event stacks monitor. So in our case, we want to sample CPU. And sampling CPU means that we want to get call stacks. And this is what this event stacks monitor basically implements. So what we can see here is the implementation of the intensive sampling mode. And again, we're not going to get inside the live stacks code. It's copied from the GitHub. Trust me that it works. And again, in itself, it deserves like a whole 2-hour talk because it's complicated. But what this gives us is the ability to connect live to an ETW source, which provides sampling of the CPU every 100 milliseconds and giving us back all the call stacks that were collected during the live session time. So we start this live session and we wait for some time. I think it's 5 seconds defined in our case. And once this is done, the session is going to have a property stacks, which is in itself is going to have a function of top stacks. That is the stacks that consumed the most CPU during this time. And then basically it's just going to write all of these top stacks into our log file. So I have the log file prepared in advance so that there are no glitches in the demo. Here it is. We can see here in the beginning that at first everything is fine. CPU is not very high. That's below 80. That's below 80. Below 80, and then something happens and it starts profiling. And we can see that it prints out all sorts of call stacks. Now, specifically in this case, we can see that this is, it's a little disappointing, but you should be aware of it. So the first call stack actually tells us that the intensive sampling itself was using quite a lot of CPU. And I am going to talk about this later before we finish. So in the meantime, let's go on to the next call stack. And here again, okay, so here we see that a lot of ASP.NET functions are taking quite a long time, which is, again, I think it's interesting to know. I don't think there's much we can do about it, or maybe we can. I'm really not an ASP.NET expert, but this is interesting information. And then finally, when we go to our third call stack, where is it? Here it is. Okay, that's our third most CPU-consuming call stacks. And here we can finally see that there is code from our application. It's consuming a lot of CPU, and it's consuming it from the account controller, which makes sense because we were trying to log in. And specifically, it calculates some hash functions, which is generally expected to maybe be expensive. So we can now go to the code, to our account controller, and excuse me, let's see which function it was. Good hash. Good hash. And we can see, and we can see that if a mail address ends with Gmail, which is exactly what we had in our demo, then it's going to compute like a very fancy and expensive hash function. So we found out the problem. Sorry. Next, we're going to see how we can diagnose memory usage problems. So the idea is going to be the same. I want to detect that I'm using too much memory, or maybe that I even have a leak if I notice that the memory is going higher and higher and higher a long time. And I would like to know what the source of the problem is. So in this case, we're not going to use ETW. We're going to use CLRMD in order to traverse the heap and find out what's taking all the memory in our memory. Moreover, if we suspect a leak, what we can do is take several snapshots of the heap with a few seconds in between and try to compare the objects and see what was freed and what wasn't. So that can help us pinpoint the problem. Another thing we can do, and I actually have a demo for this, but there's not enough time to see it, is we can use ETW to register on an allocation event. And this event can actually provide data about what type is allocated, and as I said, also the call stack of where it was allocated. So if we also monitor this GC allocation tick event for a while, we can also get information about where in our code most of the allocations were happening, which is very useful. And if you go to the GitHub, you can see the demo and the code that does just that. So let's see that in action. Again, I have a video. So this time what I have on the right is performance monitor tracking memory. And I'm trying to register to the website. And so far, okay, good. So memory has gone up a little. Doesn't necessarily mean it's a leak. But trust me, if we wait long enough, I don't want to waste any more time, the memory is just going to keep getting higher and higher and higher. So we can detect that there's a possible leak and try to figure out what's going on. So let's look at the code. This time we have our, okay, it doesn't work, leak monitor. This time, it's just a regular monitor because we're not going to collect any ETW events. We're not going to collect any call stacks. We just know that we have high memory usage, and we want to take a snapshot of the heap and see what's going on. There's no intensive sampling mode that we're going to invoke. Or, excuse me, there is an intensive sampling mode that we're going to invoke, but we're not going to collect call stacks. So this time, we're going to use the CLRMD API. And basically, what it's going to let us is that it's going to allow us to attach to our process here and collect a snapshot of the heap. And we're going to see in a moment how it's done. It's very easy. And after we collect a few of these snapshots, we are going to compare each of these snapshots to one another. And here I didn't go over all of the objects themselves. I just tried to kind of order them or organize them by type and see which type was not released from memory. So let's see how this heap snapshot works. It really is very easy. Basically, we're going to collect statistics of the number of objects by type and the total size of the objects by type. And the way that we're going to collect this data is using the CLRMD API enumerate object addresses from the heap. So that's all it takes. We just go over the entire memory space. We can get the object type. We can get the object size. We can get the name of the type. And this is just a fancy query that puts all of this data into a dictionary. There's really nothing too special about it. And once we have all of this data, it is fairly easy to just go over any two heap snapshots. It's a hard word to say. And compare what was there before, what's still there now, what's new now, and what's the difference between the two, and just print it to printing is done somewhere else, and just print it to the log file and see what happened. So let's look here. I already have it here. It's actually already open on the results, but again, we can see that at first everything is fine and memory is pretty constant, but then the code detected that memory started to grow, or in fact just surpassed a certain threshold, and now it took 3 snapshots and started comparing them to one another. So in this specific case, it's not very easy, because what eventually you're going to see is that the object that grew the most between these snapshots is byte array. And byte array is pretty generic. But if you're lucky, you're going to see that like a business-specific object became very abundant in your heap. And that's obviously going to help a lot more in trying to diagnose the issue. Now, since I wrote the code, I know what the problem is. And I know it was when I was trying to register to the website. And indeed, if I go to the registration area somewhere, well, it doesn't matter, it's somewhere here. Point is, I know where I use byte arrays. And specifically, it's right here, where I allocate byte arrays, and I save them into a static list. And so obviously, they don't get freed. And again, this is not the best example, because byte arrays are very general. But I do hope that in your own applications, you're going to have something more specific, and obviously that's going to help a lot. On to our last demo for today. That's deadlock detection. So this is going to be interesting, I think. Again, I want to detect that I have a deadlock. Now, what does it mean, detecting that I have a deadlock? It's not very clear, or at least it's not as straightforward as detecting a memory leak, because there's no single metric that tells me that I have a deadlock. So I have a few ideas here, which we can use to detect something like that, but mainly it depends on your application. But a few examples are low CPU. If your process is suddenly doing nothing, then it's possible that you have a deadlock. If requests suddenly start timing out, it's possible that the threads are busy and deadlocked, they can't answer the request. Or on the other end, maybe your thread pool suddenly starts opening more and more and more threads because like all the other threads are busy in the deadlock, so they can't handle your request, and it suddenly starts growing. So all of these might indicate a deadlock. It's not for sure, but if it doesn't happen too often, we can definitely use these metrics to trigger the deadlock detection code that we're about to see, and try to figure out if it really is something that happened. Now, in the case of a deadlock, I'm not sure that there's something we can do in real time about it. I'm not sure whether we can stop the deadlock or do anything about it. But at the very least, we can send out detailed information to the log, to the development, so they can have a look at it later. It's much better than not knowing about it. So at least that. Let's see. Again, we have a video. So this time I'm going to go to the contact page. What we see here is a CPU. So we see that the CPU is not growing, so the process is basically doing nothing. And it looks like the page is stuck. I clicked the link, but nothing is happening. So again, I can't be sure, but I suspect there's a deadlock. So let's look at the code. This time I didn't implement the basic monitoring, both because we've already seen a few examples of that and because it really depends on your application. So we're just going to jump straight into the deadlock detection code. Why doesn't it work? Oh, it does. OK. So now I want to make it smaller. And it doesn't work again. Be small. Damn you. Never mind. Go away. Go away. Go away. Thank you. Okay. So we have our deadlock monitor here. It's not any type of monitor because, again, in this specific case, I'm not implementing all the logic for the performance counters and detecting the deadlock. So basically what it's going to do is every once in a while go over all the threads and try to figure out if they're in a deadlock. And how is it going to do that? Very simply, using CLRMD, we can simply, where is it? Yes. Using CLRMD, we can simply go over all of the threads in our application. And for each of them, I'm not going to go over the algorithm. It's a pretty basic recursion. But using this simple threads property, each of these threads have an ID, and they have, where is it? And they have a list of blocking objects. That is the objects that the thread is waiting for. And each of them has a property of a, I'm sorry, that's enough. And so each of these threads have the objects that they're waiting for. And obviously this allows me, and each of these objects, yes, that's what I want to say. And each of these objects have their owners. That's the threads that own the object, own the lock. And so this allows me to write a simple recursion that goes over all the threads, reconstructs a weight graph, and detects whether there's a cycle. And once I do that, I can simply write out the cycle into our log file, and voila, we have a deadlock detected. So let's look at the result. Here we have a pre-prepared file, and so again, it all starts well, attempting to find deadlocks, all is well, attempting to find deadlocks again, and look at that, we have a deadlock. It has been detected between two threads, and this is the call stack, which is pretty cool. So specifically, the call stack points us to the home controller to process details function. Let's look at that. Home controller process details function. And well, not surprisingly, we have two locks here, first and second. And what happens here is interesting because it's actually the same function. So we call process details from inside process details, only we swap the first lock with the second lock. And so this is a textbook deadlock, which was pretty easy. I do realize that in real life, it's probably going to be more complicated, but not much more, I think. Like maybe the chain is going to be longer, and maybe it's not going to be the exact same function, but the code will write out for you the chain of the deadlock, which is, I think, is pretty cool. So that was our last demo for today, unfortunately. There are more scenarios possible out there. For example, you can monitor the fragmentation in your .NET application. And this is an important issue because the CLR is not going to compact your large object heap unless you explicitly ask for it. However, this compaction takes a long time and incurs a large overhead. So if you monitor the fragmentation in your application, you can actually make an educated decision on whether you want to compact the heap or not. So that's an interesting option. Also, we didn't see any demos of that, but you can also try to diagnose native memory leaks using ETW, because you can actually get events from allocations, from native allocations as well. You're not going to get type information because it's not the same as .NET, but still, you will have call stacks of allocations, which is interesting. And again, there are many more scenarios which would be relevant for your line of business. Before we finish, and we already saw a small example of that before, it's obvious what the advantages are. You get visibility into your application, you can scale your code without having to grow the team, but there are risks and there is a price that you pay. The first, of course, is that you add complexity to your system. It's more code, it's more things that can fail. However, you can try to reduce that risk by implementing all of this logic in an external watchdog process. Although in these demos, the code was incorporated inside my own server, none of the techniques that we used was actually, it was not mandatory. Performance counters, ETW, they're all defined and monitored on the machine level anyway. CLRMD can also attach to any process. So we could totally write all of this code in an external watchdog process. So at the very least, if something bad happens there, it doesn't affect your code. So that's an interesting route to take. Second problem is that it adds overhead. And we already saw an example of that in our log file. And in fact, I also have 2 real-life stories to share with you about this. The first is from preparing this talk. At first, all the demos were running on an Azure VM, which was pretty good, and everything went well. And then I started running the demos on my laptop in a virtual machine. And it was pretty much killing it. I had to separate the monitors from one another. I couldn't run all of them together. And you actually saw that in the log file. I had to lower all the to make the threshold higher so that it doesn't report excess resource consumption all the time. And we also had this very similar problem with a client once. He was complaining that our code was using too much CPU. So we attached a profiler, and what we found out was that all the time was spent in a function that was logging thread call stacks. And so the reason was that our process actually detected that it was using too much CPU, and so it wanted to, to output some diagnostic data. So it started writing down call stacks, but it only made the problem worse. I don't feel too bad about it though, because the machine was a laptop with a single core. We don't see much of that these days. The client obviously doesn't think like me, but you should know that it happens. And lastly, more code means more development time. But that's for you and the managers to decide whether the advantages are worth the extra time. So that's it for today. We saw that it's important to monitor all sorts of application, no matter what kind of deployment environment we're developing for. We saw how to tackle the problem using a hierarchical monitoring scheme, low overhead for detection, and higher overhead for diagnostics. And we saw several scenarios where this can be applied: CPU usage, memory usage, deadlocks. All the code is available here on GitHub. I'm guessing that the slides are going to be published somewhere, but feel free to take a photo of the link. Thank you.